Section 5. Line spectra and electron jumps. ChemTalk. Bohr's model of an atom. Electron orbits. Niels Bohr was a brilliant Danish physicist. He proposed a planetary model of the atom. He theorized that electrons travel in nearly circular paths called orbits around the nucleus. Each electron orbit has a definite amount of energy. The farther away the electron is from the nucleus, the greater is its energy. Bohr suggested the revolutionary idea that electrons jump between energy levels in a quantum fashion. This means that they can never exist in an in-between level. Thus, when an atom absorbs or gives off energy, as in light or heat, the electron jumps to higher or lower orbits. Electrons are the most stable when they are at lower energy levels closer to the nucleus. The electromagnetic spectrum. You observed light when hydrogen gas was given a large voltage. This visible light is only one part of the electromagnetic spectrum. You have probably heard of some of the other parts. These include ultraviolet, infrared, X-rays, gamma rays, microwaves, and radio waves. As you demonstrated in calculations using Bohr's model, the light from some of the transitions is in the ultraviolet region. Infrared light is also emitted as the electron jumps from E4 to E3 and E5 to E3 and other higher energy levels. Many people do not think of radio waves as being similar to light waves. However, they are part of the electromagnetic spectrum. Your eyes can see only a very small part of the electromagnetic spectrum. Often, you hear radio announcers say that they are broadcasting at a certain frequency. Your FM radio dial may have megahertz printed on the side. This tells you that the numbers correspond to frequencies in units of megahertz, or 10 to the 6th power hertz. Frequency tells you the number of cycles or waves that are being produced per second. The unit for frequency is a hertz. 1 hertz equals 1 cycle. Normally, frequency is read as per second and the cycles are dropped from the terminology. Cycles per second. Wavelength is the distance from crest to crest of a wave. The symbol for wavelength is lambda. The speed of electromagnetic radiation is constant and it is called the speed of light. Its value is 2.998 times 10 to the 8th meters per second. This is often approximated to 3 times 10 to the 8th meters per second. Frequency and wavelength are related through the speed of light. From this information, you can calculate the frequency of light of a given wavelength. The equation that is used for this is, as an example, the wavelength of blue light is 434.2 nanometers, and the frequency can be calculated as follows. As you go across the electromagnetic spectrum from right to left, you should note that the wavelength continues to get smaller as the frequency increases. Also, you should understand that the energy of the spectrum increases as you go from radio waves to X-rays or gamma rays. Max Planck, a German physicist, found that light comes in quantum or discrete packets called photons. The energy of a specific wavelength or frequency of light could be calculated. The equation he developed is where h is Planck's constant and f is the frequency. The frequency of red light is 4.567 times 10 to the 14th power hertz, which is cycles per second, which is lower than blue light. The energy of red light can be calculated as follows. So, the next time that you are standing around a campfire, you can inform your fellow campers that red light has less energy than blue light. You can also tell them how to calculate these values. Okay. Example. In hydrogen, the energy change of an electron jumping from E3 to E2 is 3.03 times 10 to the negative 19th times J. Conservation of energy insists that this is equal to the energy of the light that is emitted. You can find the frequency of the light Knowing the frequency of light, you can find the wavelength. Referring to a chart that shows wavelength and color, you find that this is red light. It is the red light that you observed when looking at the hydrogen spectrum. Calculations and units. When you make chemistry calculations, it is very important to pay close attention to the units in your answer. Look closely at the units in the example given. Do they make sense? When you calculated the frequency of the light, you used the unit for energy, the joule. You also used the unit joule seconds, J times S, joules times seconds, for Planck's constant. The resulting unit in the calculation was the hertz. How is this possible? Look at only the units in this calculation. So only look at the frequency, the joules, the seconds. Notice how the units, joules, cancel out. So here's the joules, leaving seconds to the negative first. You read earlier that 1 times the second to the negative first power equals 1 hertz, equals 1 cycle. Therefore, the resulting unit is the hertz, which is the unit for frequency. Now look at the units in the calculation for wavelength. So here's lambda, meters over seconds divided by hertz, which is the unit for frequency. This cancels out. And and you get your measure of length. The unit hertz is equal to s to the negative first power. The units s to the negative first cancel out, leaving the measure of length. In this case, it is the wavelength. Analyzing the units in a calculation is called dimensional analysis, and it is a very important tool that chemists use. Checking to see if the units make sense ensures that their calculations make sense and that they have not made an error. Use this tool as you work through all your calculations in chemistry. The photoelectric effect. Light has wave-like properties like wavelength and frequency. You observe these wave-like properties in your investigation of the hydrogen spectrum. Light also has particle-like properties like momentum and can be seen in collisions with matter. The photoelectric effect is a collision between a particle of light, a photon, and an electron on the surface of metal. The energy of this proton is calculated using the equation. The energy of light is quantized. That means that it comes in fixed amounts. In Einstein's explanation of the photoelectric effect, he showed that light must behave like a particle with fixed energies that depend on the frequency. For this, he was awarded the Nobel Prize in 1921. The problem with Bohr's atomic theory. Niels Bohr was aware that his theory of electron jumps had incredible success, but also raised some problems. Bohr's theory could only account for the spectrum of hydrogen. It could not account for the spectra of any other element. Bohr's theory could not explain why only certain orbits were allowed. It could also not explain how the electron could jump from one orbit to another. Other scientists improved on Bohr's model as they discovered more about the atom and quantum mechanics.